today we're going to be talking about basic electrical physics, like the very foundations of it. And the interesting thing about electricity is that other than like everything else, like all the other engineering disciplines, you know, like mechanical engineering, civil engineering, you can see what you're doing and you can see what's going on. You know, if there's stress on a certain piece of wood, you know, you can see it happening, you can see things breaking, you can see the gears moving and everything working. But the hard thing about electricity is that you can't exactly see what's going on. Like it's hard for us to be able to sense what's going on. So we have to use all these tools and all these analogies for us to be able to understand exactly what's going on that microscopic level. So again, so how many of you have seen these terms before, and how many of you have like seen them in a class, learned about them? All right. So can anyone tell me what voltage is? Like just in a few words, maybe like a different word for it. Like what do you guys think voltage is? Somebody's got to have an idea. You guys taking this in a class, so like in your class, like just like in general, like you can use as many words as you want. You can explain it however you want.
So like
yep.
No.
What?
Difference in potential.
Difference in potential. Good.
I was going to say like pressure.
Pressure. Yeah, you can think of it like pressure. So yeah, it's basically, yeah, you guys are both right. It's more like it's the difference in potential energy, right? So it's, you know, you can use all sorts of analogies like pressure is the difference in potential. Like so, if you have an area of high pressure, it's going to want to go to an area of low pressure. It's the same thing with like, you know, that's the difference between it. So if you're at a high point, you have a lot of gravitational potential energy. You're going to want to be falling down to a place of lower gravitational potential energy. That's good. So current. Anybody have an idea what current is? Any idea at all? So if voltage is the potential difference, what would current be? Any ideas? What? The flow, yeah. Yeah, you can think of it kind of like the flow. And then we can get into some more analogies later, but yeah, you can basically think of it as like the flow of electrons. And resistance, the third thing.
I know two of you described it earlier. Margaret, Chloe.
Yeah. I've heard you guys describe this before, so just say what you guys. They're right. They're correct.
It's the limit of like limited the amount of energy.
Right. Yeah. That's like I find kind of like the most you know, intuitive thing to think about is in like resistance. You can think like, oh, if you have resistance on something, it's just going to be electrons. It's going to be resistant, right? That's the one that like actually makes sense for words. So resistance, you know, it's kind of self-explanatory here. It resists it. Current, current sounds like flow. You know, like the current of water is like the flow of water. The thing about voltage, though, is like that's the one usually that people have the hardest time understanding because we have this word here, right? Voltage, which like voltage doesn't mean anything to any of us. It comes from the name of some Italian physicist, something Volta. So it doesn't mean anything to any of us. So an easier way to think about that is that in actually most other languages, the word for voltage translates to tension. So if you look at like German, French, Italian, all their words for voltage actually translate to tension. So if you can think of it, it kind of makes more sense as tension. So if you think about it, like when you have an area of high pressure, right? If you have like a pipe that has water in it with really high pressure, that's kind of like having water that's at like high tension. If you can think of it like that, right? So it's like high tension. And if you can think of like, so think about like when you're on the ground, right? When you're on the ground floor, this is like using gravitational potential energy. So if you're on the ground, you have like a rubber band attached to your ankle, right? So as you go up more, you're going to want to go back down, and you can feel the pull of gravity, which is like the pull of that rubber band trying to pull you back down. So the higher you get, the more tension you have. So you can think of the voltage as kind of like that. That's how you can. So the difference between two spots is like if you take a rubber band and you pull it between two spots, it has more tension. So the more difference between the two spots, the more tension it has. So that's like a more intuitive way to think of it, so you can start thinking about what it actually means to have electrical potential difference. So there's all sorts of analogies. I mean, I'm sure you guys have taken physics. I've heard the water analogy. Justin, you've probably heard of it because you used the analogy of pressure. So that's like the most basic way to think about it. It's not my favorite way to think about these things though, because it still kind of gets past everybody and it's not really the best way to think about it. So what I like to think about is I like to think of it like tension. So I like to think of it like in terms of if you have a rubber band, right? So for voltage, you're pulling it, and then, or like a spring, right? You pull a spring really far apart. The more you pull it apart, the more it's going to come together. So the voltage between two spots means that you need to have two different spots. As in, what 0 volts doesn't really mean anything as far as like absolute terms. So one spot at 0 volts, you can decide that any part, anything, anywhere is at 0 volts. And it's only the difference between that and something else that actually matters. So voltage is tension, which is the difference between the electrical potential at two different spots. Alright, so another way you can start to think about this is, let's go down to like the atomic level and think about what's actually happening with the actual individual electrons. So what's actually happening is, so when you think about electric current or like the electricity flowing through a wire, so would you think it's more like a car zooming down a freeway, or would you think it's more like if you have a line of boxes and you push one? So does anyone know which one of those is more accurate representation of actually what's going on? So as in, like, is it more, are you like basically throwing one ball down a chute? You know, you can imagine like the electricity just kind of flowing around the wire. Or is it more like where you have like a bunch of balls? Like, have you ever seen one of those like gumball, those like tubes of gumballs? And it's got like a bunch of balls in a row. And you push one at one end, and then they all move, right? So one comes out the other end. What?
The second.
Yeah, it's more like the second one. So if you think about it, like the electrons are actually not moving very fast. So the electrons are actually, it's more like if you can imagine like a row, like you have a row of boxes, right? And you push one, and then the other ones move at the other end. So like the electrons are really packed together. It's kind of like, it's like a street that has like a lot of heavy traffic on it. So it's more, it's really compact. There's a lot of electrons there, and that's how they're moving, right? So if you could think about it, in this model, the tension, that's kind of like the pressure. So like how many of them are kind of together. So if you have a bunch of them together, right, they're going to want to go to an area with just like less of them. So if you have a bunch of cars stuck together in like a really traffic-heavy area, they're going to want to speed off to an area where there's not very many cars. That's kind of like the water pressure. The current, if you could choose a point on that road, and how many cars pass through there per second, like the amount of cars that pass through there, that's the current. So that's the flow of cars. So if you can imagine through like one busy intersection, you would start to measure the flow through that intersection as how many cars go through that intersection. And the resistance is, you know, how much it's limited. So that's pretty easy to think about. You know, on a road, you could think about, you know, if it's a bumpy road, if there's a speed limit, something like that would be resistance. So now we can start to get through the relation between all these three things. So does anyone know the relation between voltage, current, and resistance? Yeah.
Voltage equals current and resistance.
Perfect, yeah. So this formula right here basically describes half of electrical engineering. That's what we're going to be going over today. So V equals IR. So you said V equals IR, which describes these things. Does anyone know what, in this equation, what the V means? It's pretty obvious. Voltage, right? What does I mean? I is current, and then R is resistance. Perfect. So here we can use this. So the amount of voltage at a certain point, right, is equal to the current at that certain point times the resistance at that certain point. So if you're looking at this right here, you have, let's say, a battery that's 5 volts, and that's going through a resistor right here, which is like, it's just like 5 ohms. So if you have this model right here, right, so you have a battery that's bringing the potential difference between these two spots, as in this spot right here is 0 volts, this spot right here is 5 volts. So this is right here, that's putting the tension into this wire, that's putting the tension through the system. That's like, the battery is what's actually pulling that rubber band apart. You know, that's what's pulling the rubber band apart, that's what making the, you know, if you want to think about like pressure, that's what's putting the pressure in the pipe, whatever you want to think of the voltage as. And then you have the current's going to be going through this wire, and this resistor right here, that's like the resistance. That's like the cars having to go through the area with the bumpy road, whatever you want to think of that as. So now that we have this formula and this model right here, can anyone tell me the current that's going through here? Or at least tell me where to start. Like, how would I start using this formula to solve this?
Voltage and resistance equals
So we want to solve for the current, right, which is I. So then all we have to do is bring this to the other side. I equals V over. Cool. So we want to find I, and we have V and R. So I equals what? What over what? Like the numbers. 5 over 5. Which equals 1. So now we know that the current through here is 1 amp. So the thing about that is, like, think of this again as in, like, you have a tube. So imagine this as one big tube, right? Like one of those tubes with the bubble gum balls in there. So right here, you have them all right there, and then this is kind of pushing them. And when you push them, they all go through here, right? So if you have all of them connected together, and when you're pushing one, are they all going the same speed, or are some going at faster speeds than others? Just make a guess. It's either or. As in, do you think what's going through this part of the wire, do you think the electrons there are moving faster or slower than the ones going through any part of it? Faster. You think faster? Anybody slower? Anybody feel the same? Alright. So they're actually all moving the same. So if you think about that, imagine you had like a big huge tube, and you push one at one end, then you're pushing them all at the same speed because they're all connected to each other. It's kind of like those little Newton cradles, where you hit one and it transfers energy to them all. So if you can think about that, so the pressure is different in different areas, but they're all moving at the same speed. That's why at this point you have a higher voltage than here, but the current through this whole loop is all going to be the same. So the current through any part of this is the same. So the current here that we've discovered, 1 amp, is through this whole part. This is all 1 amp. So if you think about it, if we're to, like, let's add another resistor. Let's add that and make it 1. So the current that's going through here is going to be the same as the current that's going through there. Right? So the voltage drop is different between these because the tension is going to be using this 5 volts right here. So like right here you're going to get different voltage, there's different voltage drop across this resistor, but because they're all on the same line, because they're all part of the same tube, all the electrons, there's like a bunch of them. When you push one right here, it's going to push them all at the same speed. So if you have one loop like this, all the current through it is all the same. So when you solve for that current using V equals IR, it's the current for this whole loop. So does anyone know how to add resistors? Yep.
If they're in series, you just like add up the value.
So what does that mean, series?
Series is like they're connected like in the same circuit, like,
Right.
as opposed to parallel.
Yeah, so you see these words series and parallel, right? So how many of you have heard these terms before, series and parallel? All right, cool, most of you. All right, so series means that you have your resistors hooked up like this in one line, right? So that's all one line, all one tube. It means the current through it is all going to be the same. And then parallel means that you have them like this. So you're splitting up the line, and now you have 2 lines that are at the same, right here. See, they connect here, they split off, go to 2, and they come back together. So that's considered parallel. So that at that point, you actually have 2 different tubes. So the current through the different lines can be different. Yeah, so in this case, would this be series or parallel? Series, right? So this is resistors connected in series, which means that if you, as we heard Margaret say earlier, when you add resistors in series, what do?
You just add up the numbers.
You just add up the numbers. So like, what's the resistance through this whole, like from here to here, what's the resistance? 6 ohms, right? So this is the same as writing, I don't know if you guys can see this. That's the same as writing this, because these 2 resistors add up together to create, it's basically one big resistor of 6 ohms, right? So now, if we have this right here, in this system, what's the current going through the loop?
6. 5, 6.
5, 6. Because if you look at it, you have 5 volts equals current times 6. So I equals 5, 6. Right? And so that 5, 6 amps, is that the current through here or the current through here? Which resistor has 5, 6 amps going through it? Maybe. Just make a guess.
Wouldn't it be both?
Both, exactly. Right? So both of them have the same amount. The 5, 6 amps that goes through them is the same for both of them. So I know there's like a billion analogies you can use for this, and like any one analogy isn't really gonna be enough for you guys to understand it. So we have like the car, we have the bubble gums in the huge tube, we have the water pressure. Another way you can think about it is, let's say you have a rope that's being pulled, right? And the rope's being pulled through this whole thing. So if you add some resistance, that's like pinching the rope. So if you have a rope that's moving, right, it's going zzz, and you pinch it, you're going to start feeling it, right? And it'll start slowing up the whole line. So if you add more resistance to one part of the line, it's going to slow up the whole line. So we added 1 ohm down here, and that slowed the current up here down to 5, 6 amps, whereas it used to be 1 amp. Because if you can think about that, if you're pinching it a little bit, so that's like, let's say that we have in this rope, someone pinched it with like 5 ohms worth of pinching, right? And then down the line, someone pinched it again with like 1 ohms worth of pinching. So together they're going to be slowing it down to about 6 ohms worth of pinching. And you can feel the energy coming off of that as heat. Because when you do that, it's probably going to hurt. It's going to get pretty hot. Okay. So now parallel. So if series works like this, if you add them up like that, and that equals to 6 ohms, what if I was to do what if I instead put that 1 ohms right there? Does anyone know how to add them up? As in, like, what kind of rewrite this as? Like, what's the total resistance from here to here? Anybody know how to add them up in parallel? Okay. Yeah. Where'd you get to 5, 6 from?
So it's like 1/5 plus 1 over 1 to the negative 1.
Yep. So the total resistance through here, let's call that.
Have you done this before?
Yeah.
Yeah. Let's call that. Okay. So the total resistance through there, let's call that RT equals. Yeah, like this. So 1 over that equals 1 over 5 plus 1 over. So you take 1 over the first line in your parallel circuit plus 1 over the next line in your parallel circuit, and then that equals 1 over. So if you want to do it, for here we do 1 over RT equals 1 over 5 plus 1. Anybody know what 1/5 plus 1 is? 1/5 plus 1.
You guys gotta step up a little bit now. Come on. What is 1 plus 1/5?
Yeah. 6 fifths, right? So equals 6 fifths. So 1 over RT equals 6 fifths. So what does RT equal? 5, 6, right? So you just flip. So here in there, RT is 5, 6. So if you think about that, so if in the earlier one it's the rope, right? And you pinch one part of the rope and you pinch another part of the rope, you're going to slow it down for the whole loop, right? But here what you're doing is you're giving another path for the electrons to go through. So like now, you're saying that they can go through either here or they can go through here. And it's because the electrons are being given a choice. It's like when you're going on the freeway or like a street, right? A busy street. And then there's a bunch of traffic on one spot, right? But now they've opened up a new lane. So now, like, let's say they open up a new lane that's like a lot faster, several more lanes in it. Of course, like half the traffic's going to go over there, probably more. So between all the electrons that have decided to go through the easier way and the ones that are still going through this way, now you can see the resistance has been diminished. Now the resistance is less than even either of them individually. So whereas before you added them and it made it more resistance, it upped it to 6 ohms. Now that you've added another path for them to go through, Now you've actually brought it down to 5/6. So can anyone say the current going through here? What's the current coming out of the battery now? Or how would I set up that equation? Anybody? We've done it before. So where do I start? I start with V, right? What's V? Right. And then I is what we want to know, right? So what's R? The R of the whole system that we just figured out. 5/6, yeah. So what's I? 6. So that's huge right there, right? So before we had 1 amp, then we brought it down to 5/6 amps, and now we're gone all the way up to 6 amps, which means that there's a lot more flow going through. And if you think about it, it makes sense because now the electrons, rather than having to go through this one area, which is like a pretty, it's pretty high resistance right here. It's a pretty bumpy road. It's a pretty, thin piece of pipe that the water's having to go through. Now you've given them another path that's a lot less resistive. So it's another path of the resistor for all the electrons to go through. So now when they get here, some of them are going to go through here, some are going to go through here. And if you think about it, all the ones coming out of here are now 6 amps worth of electrons. Because the current, remember, is deciding, okay, like let's say at this point, if you draw a square around that part of the wire, how many electrons are flowing through at any one time? So you have all the ones that are flowing through here, plus all the ones that are flowing through here, because now you have a bunch going through here. And before they split off like that, through that part of the wire, you've got 6 amps worth, which is a lot more flow. So that's why, let's say, a resistor you can think about, so this voltage source right here, you guys can easily think of that as like a battery, right? It makes sense that the battery would bring you up to that voltage. So what's like a resistor? What acts as a resistor? Like what is a resistor in a circuit? Any examples of what it might be?
Light.
Light, right? So like a light bulb. A light bulb would be a resistor because it's providing an area of the wire that the electrons are having a harder time to flow through because they're trying to dissipate the energy off as light. So if you look at these as light bulbs, right? If you look at them as light bulbs, I'm going to give you guys 2 different circuits right now. So in which one are the light bulbs brighter? This one? The parallel, right? Because it's got more current, more amps. Yeah, so if this one's got, like, let's say that this was like a 5 ohms one, like the resistors that we used in the previous example, this one would only have 5/6 amps going through both of them. This one would have 6 amps going through both of them, which means this is going to be significantly brighter. You actually have to watch to make sure that your light bulbs can handle 6 amps, because that's a lot of energy. So a lot more energy is going through this one, and this one. And you can figure that out using this equation. V equals I naught. You can use it for anything. That's the basic foundation of basically like half of electrical engineering. Is like different forms of V equals I naught. You guys have seen 2 different forms right here, and they can get a lot more complicated than that. So when you guys are building your circuits and you're looking at it, and you see these different circuit layouts, some of them parallel, some of them series, and you want to know exactly what's going on, this is a basic idea. So to recap, what can you think of voltage as? What is voltage? Tension. So can anyone give like a basic analogy for that? Like using any of the analogies, what would voltage be?
A rubber band.